Students, let's start with our next topic, that is conservation of mass. First, basic principle for fluid mechanics. So here continuity equation, here physical principle is what? Mass is conserved, which follow conservation of mass principle. So if we have to write in short way how to write our conservation of mass principle, so there is very simple way that let us assume this is our bank, and if we are depositing some amount, we consider as our inlet flow, and we are withdrawing some amount. If we are withdrawing some amount, this will be your output, and there will be some change inside this control volume. So whatever change inside this control volume, that will be considered as some interest. After some time there will be some net change inside the control volume, so that will be resemble with our some interest rate in our banking. Okay, so if we see this banking procedure, so this will be very similar to our conservation of mass also. So here some mass fluid entering, some mass fluid out, and there will be some change inside the control volume. So if there will be positive in out, though there will be negative change. Okay, so in this way there will be conservation of mass principle. So now if we for our simplicity, if we have to arrange this fluid flow, so there are four models if we see here. So model of the finite control volume fixed in space, model of finite control volume moving with flow, then model of infinitesimal small element fixed in space, and model of infinitesimal small element moving with flow. Okay, so for simplicity we first start with our model of infinitesimal small element fixed in space. So although all the models are interrelated mathematically, but we focus in simple way. Okay, so wherever we understand simply and easiness, so that will be preferred. So model of infinitesimal small element fixed in space, we start with that. Okay, so first model of infinitesimal small element fixed in space, model of infinitesimally small element fixed in space. So this is our control volume, let us assume. Okay, so in this control volume, so there will be inlet and outlet in x direction, similarly inlet and outlet in y direction, and there will be inlet and outlet in z direction. So for inlet, if we have to write for mass flow, so mass is what? Mass upon volume equal to density. So density into volume, this is nothing but mass. And again if we solve for volume, so volume equal to what? Velocity into length. So this will be your volume. So volume it is equal to velocity into length. How it will be velocity into length? We can write it. So see, volume is equal to what? Area into length. And if I divide with this, so this will be area. So if we divide with time, because mass flow rate, it is nothing but what? Rate of change of mass. So rate of change of mass means what? Rate will be indicated with time, per unit time. So area into length, it is volume per unit time. Okay, so length upon time, it is nothing but your velocity. So area of cross section about which fluid is flowing. So if I see inlet, so how I write this inlet? So inlet will be what? Rho for x direction velocity equal to u. Okay, see, for x direction velocity, we consider u as our notation. Y direction velocity, for x direction velocity u, and y direction velocity small v, and z direction velocity is w. Okay, so in this way we proceed here. So rho u, So for infinitesimal small element, let us assume dx, dy, this will be dy and dz. Okay, so what will be cross sectional area? Cross sectional area will be what here? Dy into dz. So this will be our cross sectional area, dy into dz for inlet. And similarly for outlet, so for outlet we will use Taylor series expansion. So for Taylor series expansion, rho u plus del by del x, rho u into dx, and area of cross section will be same, dy dz, dy dz. In the same way for y direction velocity, density into velocity in y direction, that is small v, and then area of cross section, it will be dx into dz. Similarly for change in y direction, so rho v plus del by del y of rho v dy, and then cross sectional area will be same. So this is cross sectional area for y direction, so dx into dy, dx into dz. Okay, so similarly for z direction, if I have to write, so rho w into z direction, it will be dx dy area. So this is nothing but your dx dy area. Okay, and similarly for outlet z direction, so there will be Taylor series del by del z, rho v dz, and then dx dy. So this is all about the inlet outlet. So just like your bank, you are withdrawing some amount and you are depositing some amount. There will be some interest rate inside this bank. This will be net change inside the bank. So in this way there will be a conservation of mass principle here also. So in the same way, if I have to write this in mathematical form, so how I can write this in mathematical form? Net mass flow, okay. So net mass flow, it will be what? In minus out. So in minus out, so for rho u dy dz, this is inlet. Similarly for outlet, this will be in minus out, so out will be what? Rho u plus del by del x of rho u dx, and then dy dz. So these two will cancel out, finally minus del by del x rho u dx dy dz. So now this negative sign indicates there is decrease. Okay, so this is all depend on your direction only. So don't focus on this negative or positive sign. If we take out minus in, so it will be positive. If it will be in minus out, so it will be negative. So okay, this is vector dimension according to vector dimension. Okay, so net mass flow in x direction, this will be in x direction. So net mass flow in y direction will be what? So directly I am writing net mass flow in y direction. So net mass flow in y direction, it is equal to minus del by del y rho v dx dy dz, and net mass flow in z direction, so it will be minus del by del z rho w dx dy and dz. So in this way there will be a net change inside the control volume. So how I can write this net change inside this control volume? So net change inside control volume, this will be again minus del by del t of rho dx dy dz. Now rho, it is what? Density. Dx dy dz, it is what? Volume. So density into volume divided with time. So this is net mass flow, whatever change occur inside the control volume. And if I write this complete equation in one complete sentence, so how I can write? So finally this will be positive, so del by del t, first I write this. Okay, then dx dy dz I cancel out from every From every term I am cancel this dx dy dz, and finally I will write this equation. Okay, this is equal to 0. Okay, this is nothing but net change inside the control volume. Okay, finally del rho by del t plus rho. See, rho it may be variable or it may be constant. If rho it is constant, then your fluid will be incompressible fluid, and if rho it will be it vary, then we can say our fluid it is compressible fluid. Okay, so now how I can write this? I can directly write this gradient of rho v, it is equal to 0. Okay, so this is nothing but your continuity equation. Okay, for infinitesimal small element fixed in space. Okay, so if I have to write continuity equation for infinitesimal small element moving with flow, then please try with yourself. I am directly writing here del rho by del t plus it will be rho gradient of v, it is equal to 0. Only this change will be there, and this will be capital D by capital dt. So how it will be, we will later on see this part. Okay, so about continuity equation, there are total 4 models we have. First, infinitesimal small finite control volume fixed in space. Okay, this will be integral form. Finite control volume moving with flow, this will be also integral form, but this is, if finite control volume moving with flow, it is non-conservative in nature. If finite control volume fixed in space, it is conservative in nature. Okay, although mathematically this both conservative form and non-conservative form has same meaning. Okay, because mathematically we can convert conservative form into non-conservative form, but there will be physical significance, different physical significance for conservative and non-conservative form. Okay, so during our Navier-Stokes equation we will understand that conservative and non-conservative in detail. Okay, so this is all about our continuity equation. So this is our continuity equation based on infinitesimal small element fixed in space. This is continuity equation, infinitesimal small element moving with flow. This is partial differential form continuity equation, which is conservative in nature. This is also partial differential form continuity equation, which is non-conservative in nature. And with the help of divergence theorem, we can convert these two forms. Okay, interchange these two forms. Okay, thank you very much.